I will be talking about proving lower bounds for testing complete positivity and quantum separability. And this is joint work with Ryan O'Donnell. We will consider distributions over the universe omega defined as the d by d grid, which consists of all pairs of numbers from 1 to d, where d is some positive integer. We will think of distributions on omega as d by d matrices, where the ij entry of the matrix defines the probability of the pair ij. And we will say that a distribution P on omega is completely positive if it can be written as a convex combination of distributions of the form V times V transpose, where V is a distribution on bracket D, which we think of as a column vector in RD. So for example, the uniform distribution on omega is completely positive because it can be written as V times V transpose, where V is the uniform distribution on bracket D. Now let P be an unknown distribution on omega and consider the following problem. Suppose you have sample access to P. You want to decide with high probability if P is completely positive or epsilon far from all completely positive distributions on omega in total variation distance. And the task is to solve this problem using as few samples from P as possible. This problem is motivated by the problem of testing quantum separability. So a quantum state rho on CD, and here you should think of CD as bracket D in the classical case, is a D by D complex matrix, which is positive semi-definite and has trace 1. So basically the eigenvalues of rho form a distribution on bracket D. Now a quantum state on CD tensor CD, so the quantum equivalent of omega, is said to be separable if it can be written as a convex combination of products of quantum states. Just so. So for example, the maximally mixed state, which is just the identity matrix normalized to have trace 1, is separable. Now, let rho be an unknown quantum state on CD tensor CD, and suppose that you have measurement access to unentangled copies of rho. The problem of testing quantum separability is to decide, based on the measurements of copies of rho, if rho is separable or epsilon far from all separable states in trace distance, where trace distance is the quantum version of total variation distance. And the task is to solve this problem using as few copies of rho as possible. Now, in our paper, we showed that testing complete positivity requires d over epsilon squared samples from P. We do this by reducing to the problem of testing whether P is the uniform distribution on omega or epsilon far from all completely positive distributions on omega. Using a similar approach, we showed that testing if a quantum state rho is separable requires d squared over epsilon squared copies of rho, as long as epsilon is not too small. Because of our approach, where we test if rho is actually the maximally mixed state or epsilon far from all separable states, epsilon cannot be too small, because we know that if a state is too close to the maximally mixed state, then it automatically becomes separable. Finally, we showed that learning a completely positive distribution on omega to epsilon additive error and total variation distance requires d squared over epsilon squared samples, which indicates that our lower bound for testing complete positivity is probably not tight. So for the rest of the talk, I will sketch the proof of the following result, which is that testing if an unknown distribution P is the uniform distribution on omega or epsilon far from all CP distributions on omega in total variation distance requires d over epsilon squared samples from P. And it is easy to see, because the uniform distribution is completely positive, that this implies that testing complete positivity requires the same amount of samples. Now, let CP omega denote the set of all CP distributions on omega, and let x1 to xn denote the n samples that we get from the distribution P. By a test for uniform or far from completely positive, we essentially mean that we want a decision algorithm that might be computationally inefficient but it has to satisfy the following property. If the samples x1 to xn come from P, which is the uniform distribution, then the algorithm T must accept with probability at least 2/3. And if the samples come from a distribution P, which is epsilon far from all completely positive distributions, then the algorithm cannot accept with probability more than 1/3. Another way to formulate this condition is to say that there exists an event in omega to the n such that the uniform distribution on omega to the n gives the event E probability at least 2/3. And for all distributions P, which are epsilon far from completely positive, the probability of the event E on P to the tensor n is at most 1/3. So the technique that we will use to prove our lower bound is as follows. We will construct the distribution dn on omega to dn as a convex combination of a family of hard distributions, which are epsilon far from being completely positive. Then, if E is an event corresponding to a test for uniform or far from completely positive, then we know that its probability under the uniform distribution over the n sample is at least 2/3. And the probability of E under dn will be at most 1/3, because all the probabilities P1 to Pk are epsilon far from Cp. Hence, we will obtain that the total variation distance between dn and the uniform distribution is at least 1/3. So all we have to show now, having defined dn, well, is that the total variation distance between dn and the uniform distribution being at least 1/3 implies that n is at least d over epsilon squared. So how do we define dn? Well, we need to define the family of distributions which are far from Cp omega. And we will do that as follows. For each subset of 1 to d, of size d over 2, we will define a density phi sub s, which gives weight to 1 plus epsilon for all pairs ij, where I is an s and j is an s complement, or vice versa. And it gives weight 1 minus epsilon to all the other pairs. Now we note that phi sub s defines a density function with respect to the uniform distribution. So we can define a probability p sub s as this distribution p sub s as the distribution defined by the density phi sub s. So now we have to show that each of these probability distributions p sub s satisfies the property that it is epsilon far from all the Cp distributions on omega. And the proof goes as follows. We will let x be a vector, a d-dimensional vector with +1 and -1 entries, and it is defined as follows. xi is equal to 1 if I is an s, and xi is equal to -1 otherwise. Now, if q is a completely positive distribution on omega, then the quantity x transpose qx will be equal to a convex combination of non-negative numbers, which is going to be non-negative. Moreover, you can check that x transpose p sub x sx is equal to minus epsilon. So first of all, p sub s cannot be completely positive. And furthermore, because the total variation between p sub s and q is bounded below by the difference of these two quantities, we obtain that, and q is arbitrary, we obtain a total variation distance between each p sub s and q is at least epsilon over 2. So therefore, p sub s is epsilon over 2 far in total variation distance from the set of all completely positive distributions on omega. So now we just define d sub n to be the average of all distributions of the form p sub s to the n. So essentially, you can think of dn as you pick a random distribution p sub s, and then you take n IID samples from it. Now we want to show that if the total variation distance between dn and the uniform distribution is at least 1/3, then n is at least d over epsilon squared. So following some calculations, we will arrive at the following inequality. The initial calculations are essentially symbolic manipulations. And this is the crux of the proof, where we can bound the 2 times the squared total variation distance by a quantity involving this probability, where S and S prime are random subsets of 1 to d of size d over 2, and R is the size of their intersection. So we need to understand, we need to upper bound this probability. Now, R is distributed being the intersection of 2 subsets of equal size, the size of the intersection. It is distributed as the hypergeometric distribution with the d over 2 draws from a set of d elements with d over 2 successes. And for this distribution, we have the following concentration inequality, which holds. So now we apply this concentration inequality to our upper bound, and then solving the integral, we obtain that 2 times the squared total variation distance between dn and the uniform distribution is upper bounded by a quantity 1 over c minus 1, where c is d over 4n epsilon squared. So rearranging terms and using the fact that the total variation distance is bounded below by 1/3, we get that n is at least d over epsilon squared. And that completes the proof that testing if a distribution is uniform or epsilon far from completely positive distributions requires at least d over epsilon squared samples from the distribution. In the quantum case, we prove similarly that testing if a state rho is the maximally mixed state, which is the analog of the uniform distribution, or epsilon far from all separable states, requires d squared over epsilon squared. And since in the quantum case, a bipartite state is determined by d to the 4 parameters, and in the classical case, a distribution over omega is determined by d squared parameters, then we obtain a typical scaling where the sample complexity in the quantum case increases quadratically with respect to d in comparison with the complexity in the classical case. And that is it. Thank you.